In this lab, you'll be doing an extended series of problems involving acid-base equilibrium. The first problem set involves reacting a strong acid with a strong base, and you will do that before the equivalence point, at the equivalence point, and then after the equivalence point. It's worth noting that in these two situations, one or the other will be in excess. So either your strong acid will be in excess here or your strong base will be in excess here. The flip side would occur in this third scenario. Either your strong acid would be in excess or your strong base would be in your excess. And obviously at the equivalence point, the concentration of your acid will equal your concentration of your base. Since both of these are strong acids and strong bases, they neutralize each other. In fact, mostly at the equivalence point between a strong acid and strong base, you have what's called a neutralization reaction. That is to say, a strong acid will neutralize a strong base. And in that scenario, your pH is going to equal to 7. That's the simplest scenario. Now, you have to determine whether you have a strong acid or strong base in your problem before you can automatically state that we're at the equivalence point. And you have to make sure that the calculated concentrations are equal. So first of all, let us know what constitutes a strong acid versus what constitutes a strong base. Anything else would be either a weak acid or a weak base. Our strong acids, there's generally 6 of them that you should just go ahead and memorize. So if you memorize these 6 or so strong acids, then everything else will be a weak acid. And generally we consider strong acids will go to approximately 100% ionization to the hydromonium ion or H+. So we have the acid dissociation constant going to be much greater than 1. A very positive number for the acid dissociation constant for the forward reaction. What are the chemicals that are strong bases? So here you want to look at group 1 or group 2 hydroxides. Group 1 or group 2 in the periodic table and their hydroxide components. So those would include your lithium hydroxide, your sodium hydroxide, that's your prototypical strong base, your potassium hydroxide, rubidium hydroxide. Notice all of these counter ions belong to either group 1 or group 2 in the periodic table. Cesium hydroxide, strontium hydroxide, barium hydroxide. Here you're going to have a Kb, the base dissociation constant, be much greater than 1, and we would expect, as in the same situation with a strong acid, we would expect 100% ionization to the hydroxide ion. Well, this one will just as much neutralize that one as that one will just as much neutralize this one, and you have a situation where the pH is 7. And the net ionic equation for that is just water. H plus, the ionization of water. H plus OH minus goes to H2O. So that's what we would call the net ionic equation. So after you do a set of these problems, you'll move on to a situation where you will have a weak acid reacting with a strong base. Before the equivalence point, at the equivalence point, and then after the equivalence point. So what do you think would happen if you are before the equivalence point? Okay, so usually what would happen is that the strong base would consume all of the weak acid, and then at the equivalence point, the concentration of your strong base, such as your hydroxide, sodium hydroxide, lithium hydroxide, your hydroxide, would equal the concentration of your weak acid, any acid that is not part of our 6 here. So what do you think is going to happen here? Well, you're going to have to use your classic ice table. And it's not just the ice table for the reaction that you're talking about, because this is going to equal to that. You're going to have to do the ice table for the reverse reaction if you want to determine the pH of the subsequent solution. We'll do an example of this to better illustrate that phenomenon. And then then you'll do a third set of problem, a third subcategory where the strong base is after the equivalence point reacting with the weak acid. So one of these is going to be an excess, either the weak acid or the strong base. And then finally, the strong acid will react with a weak base before the equivalence point. So we would imagine the strong acid would play a role in consuming or subsuming all of the weak base. At the equivalence point, you'll have a situation where your concentration of your strong acid will equal to your concentration of your weak base. So a classic example of a weak base would be the NH3 or ammonia, excuse me. That's our classical example of a weak base. So if those two concentrations are equal, we'll have to do an ice table. Because this will neutralize that, their concentrations are equal, we're actually going to do an ice table for the reverse reaction. And then we will do a problem with the pH, where we will find the pH of a strong acid and weak base after the equivalence point. So in most of these problems, you will have to use an ice table. So be cognizant of that. Instead of using an ice table, you can just go ahead and use your straight up pH or pOH equation. pH is equal to minus the log of the hydromonium ion, or pOH is going to equal to minus the log of the OH concentration. And then you're going to work with some problems involving solubility of a sparingly soluble compound. We will do one set of problem involving the common ion effect, and then problem set involving complex ion formation. But one of them is going to be an excess. We don't know which one. So in this problem, we are asked during the titration of 10 mL of 0.150 sodium hydroxide, that immediately should ring a bell with you as something that constitutes a strong base. You add that to 50 mL of 0.2 molar nitric acid. Automatically you should start hearing in your head strong acid, because that's one of our 6 examples of strong acids and strong bases. So you're going to have a neutralization reaction. Does that mean your pH is going to be 7? Well, not necessarily. We're going to have to do some calculations here. First thing we want to do is figure out the concentration of OH. Concentration of hydroxide. Notice I'm omitting the sodium. The sodium is just a counter ion. Sodium hydroxide is completely soluble, so it will dissociate in water, in aqueous solution, into the sodium ion and hydroxide ion. So the concentration of the hydroxide ion here is going to be 10 mL. You took 10 mL of a 0.150 molar solution of NaOH. I'll just say OH minus. That is the concentration. And out of that concentrated bottle, you took out 10 mL. And you're dumping it into a solution that has a total volume of what? It has a total volume of 10 mL plus 50 mL. So you have a total volume of 60.00 mL. That's your total volume in this new solution. So my final concentration is going to be 0.025 molar. You can notice here my units cancel, the mils here and the mils here cancel. I'm left with units of molar hydroxide. Let's do the same thing with nitric acid. Notice I'm not concerned about the NO3 minus. The NO3 minus here, just like the sodium ion here, are what are known as spectator ions. They're not really going to participate in any acid-base reactions. So the concentration of H+, what do we have here? We have 50 mL of a 0.2 molar HNO3, so 50 mL, and we took 50 mL out of a bottle that it has a concentration of 0.200 molar, so I'll just put H+ here, knowing that my nitrate is a counter ion or spectator ion. What's my total volume in the solution? My total volume in this new mixture is going to be 10 mL plus 50 mL, and that is going to be the same as before, 60 mL. So what's my new concentration of H+, the hydromonium ion? Notice the mils and mils cancel, so I have 0.167 molar H+. That's my new concentration of hydromonium ion in the mixture, and this above is my new concentration of hydroxide ion in this new solution that I've made. So are we at the equivalence point? The answer is no, because one of them has a concentration of 0.025, the other one has a concentration of 0.167. So what is the pH of this solution? Which is in excess here, and which will get subsumed or consumed up first? Strong base hydroxide ion is going to react with my strong acid. Strong will like to neutralize the other strong. It's a battle of strength. Who's going to be left over, and what's going to get all consumed up first in the battle of strong acid versus strong base? This is going to get all eaten up, leaving behind a remainder of acid. Well, this 0.025 molar hydroxide ion will react with 0.025 molar hydrogen ion. In other words, the 0.025 molar of the strong base can react and can only neutralize 0.025 molar of the strong acid, leaving behind some residual strong acid. So how much strong acid is left over after neutralization? It's going to be 0.167 molar H+, because this is going to be in excess, minus 0.025 molar that neutralized the base that's available, and all the strong acid will react with all the strong base, is going to be my residual concentration of hydrogen ion that has not been neutralized. So now what's the pH of the solution? Well, for a strong acid or a strong base, I think I alluded to this before, you don't really need to use the ice table, okay? Because you're dealing with a strong acid in nitric acid, close to 100% or 99% of nitric acid is going to be 99% H+, or the hydromonium ion. So you can just straight up plug it in to your pH equation. pH is equal to minus log of the hydromonium ion, or H+. And in a strong acid, this is going to be 100% hydromonium ion. So our concentration after neutralization of whatever base that's in our solution, it's going to be minus the log of 0.142 molar. And when we do that, that should yield us the answer to this problem. So minus the log of 0.142 molar, I'll do that in my calculator. In my calculator, you just go log, and then I'll just put a parentheses here, 0.142 close parentheses, and it's minus the log, so I just remove the minus sign, times minus 1.847, and so my correct answer here is 0.847, 0.848. There's no units in my pH, so it's just a measure of hydrogen ion concentration, and that's pretty acidic. Attempt this problem here where we're asked to find the pH of the equivalence point in which 25 mils of 0.2 molar C6H5COOH, that is benzoic acid, with 0.2 molar sodium hydroxide at the equivalence point. So benzoic acid, you have to ask yourself the question, is this a strong acid and an easy source of protons, or is it a weak acid and a relatively weak source of protons, henceforth you'll have an equilibrium? It's not part of our list of strong acids, so we have a weak acid in benzoic acid. And what are we reacting it with? We're reacting this with sodium hydroxide, which we know by now is a strong base. So if we have a weak acid, the Ka value is something that we have to take into account when determining how well this particular acid is going to give off that proton. So in order to do this problem, we'll need the Ka value of benzoic acid. Ka for benzoic acid is going to be 6.5 times 10 to the minus 5. So that constitutes this equation, C6H5COOH plus, this is an aqueous solution, plus water. 10 to the minus 5 means it's probably not going to go 100% towards the product side, but we still may get some generation of H3O+. Now, I'm just going to write it as H plus instead of H3O plus. And then C6 H5COO minus, the conjugate base to this conjugate acid. When we have a bottle of benzoic acid sitting around in the lab, we will have some of the fully protonated form, benzoic acid. We may have some of the deprotonated form, that is called benzoate, would be the conjugate base. And the magnitude, how fast this reaction proceeds, this forward reaction, is given by Ka, the ability to generate hydromonium ions, H3O plus or H plus. And as I stated to you before, we have that value at 6.5 times 10 to the minus 5. So that's the reaction that we are doing, we're considering, but what we have done is we've added some NaOH to it. A strong base is going to react with a acid, in this case a weak acid. Now the problem throws a kink here because it's asking for the pH at the equivalence point. So what is the pH at the equivalence point? The equivalence point is when the concentrations are equal to one another. So if you have 25 mils, that's my V1, use this equation here, M1V1 equals M2V2. If you have 25 mils of my weak acid, whose concentration is 0.200 molar, equivalence point, they have to equal one another. This relationship must stand. So I'm going to solve for V2, which would be my volume of strong base. What's my concentration of strong base that I am reacting it with? I'm reacting it with 0.200 molar. So here is my OH component. Here is my benzoic acid component. The equivalence point, these two must equal to one another. And when you do that, you'll notice that the mils will not cancel, but the molar will cancel. You're left with the final units of mils. And the final answer is that it takes 25.00 mils of 0.2 molar sodium hydroxide to neutralize 25 mils of 0.200 mil benzoic acid. Well, no duh, right? 25 mils of 0.2 molar sodium hydroxide will neutralize 25 mils of 0.2 molar benzoic acid. This is an important point. You don't want to neglect this. If you want to be a little bit more judicious here in figuring out your final concentrations. This is what you want to do in all these types of problems, in fact. So let's first look at our final concentration of benzoic acid. 25.00 mils. Took that volume out of a bottle whose concentration is 0.22 molar of benzoic acid, and we put it into a new solution whose total volume is what? Whose total volume is going to be 25 mils we took out plus the 25 mils that we have to add to get to the equivalence point. So 25 mils plus the 25 mils is 50 mils. So my final concentration is going to be 0.100 molar of benzoic acid. And because we're at the equivalence point, the concentration of my strong base, OH minus, is going to be exactly the same thing, and it's going to be 0.100 molar. So this is what's essentially the definition of the equivalence point, but what's the pH now? Okay, so let us write what is actually happening here in the form of an ice table. COOH, I reacted that with strong acid sodium hydroxide. Is in equilibrium. Strong base will eat up all of my weak acid, and what do bases do? Bases like to abstract protons, so 0.100 molar is our initial concentration. We added that to a solution that contains hydroxide ion. What is the concentration that we calculated before? We also calculated that as 0.100 molar. Initially this is 0, initially this is 0, or we're not concerned with that. All of this happens in water, so water is everywhere because that's the solvent where all of this stuff is going to happen. And what's going to occur? Well, all of the hydroxide is going to get eaten up because it's a strong base. You're left with 0.100 molar of the benzoate, it's just water. And you're left with 0 of the benzoic acid. You're left with 0 of the hydroxide ion. And you're left with 0.100 molar of the conjugate base benzoate. Conjugate acid, here's our conjugate base. The question is asking for what is the pH. We determine the pH. We cannot use the Henderson-Hasselbalch law because if you remember the Henderson-Hasselbalch law is pH is equal to pKa plus log of the ratio between the conjugate base to the conjugate acid. We can't do that because our HA, our conjugate acid, is 0. You cannot have 0 in the denominator. So how will we get the pH is our conundrum here. Well, look at the arrow here, okay? The arrow, as in all equilibrium problems, means that it does not go to 100% completion. The same way in solubility equilibria, we will have some proportion. Now, we don't know how much. We don't know if it's 50, 60, 70%. Usually the Ka and Kb magnitude tells us this. But some of that reaction will occur in the back, okay? So in a situation where you are at the equivalence point, okay, so now let's take a look at the back reaction. This is the forward reaction where all of the weak acid gets eaten up. It's a weak acid, so some of that weak acid can get reformed by the back reaction. So let's do the back reaction. Now you have some hydroxide ion. This has a Kb value. Kb is nothing more than, by virtue of this relationship, Kw is Ka times Kb. Remember, Kb is the autoionization of water. So the Kb here is 1.54 times 10 to the minus 10. So that is the equilibrium constant, the Kb, for this back reaction. So now let's do our ice table. Our ice table one more time. Remember, in our first ice table, all of the weak acid was eaten up by all of the strong base. Now, in the back reaction, some of that weak base, or some of that base, is going to pick up a proton from water. So we found out that the concentration initially formed from the concentration of this is what we're going to find. Now the concentration of this, not 0, because now I'm using the back reaction. So I'm trying to find for the concentration of benzoic acid from some of this reaction going the other way. To do that, I'll label this as 0, and I will label this as 0 again. Minus x, this will be plus x, plus x. Equilibrium, I'll have 0.100 minus x. Here I'll have x, and my hydroxide ion will also be at x. My equilibrium constant, E value, I have determined through my Kw expression as 1.54 times 10 to the minus 10. That will equal to the concentration of equilibrium at equilibrium of my products, that's x. First, this one will also be x, and the concentration at equilibrium for my reactant, products over reactants, my reactant is going to be 0.100 minus x. So further manipulation, I'll get 1.54, my Kb, times 10 to the minus 10 is equal to x squared divided by 0.100 minus x. Now what I can do here is assume x is small because 10 to the minus 10 is such an insignificant number. Remember, the larger this number, the more the reaction is going to proceed this way. The smaller this number, the more the reaction will just stay right here towards the reactant side. 10 to the minus 10, it's a fairly good assumption that my change x is going to be very, very small. Who knows, 10 to the minus 5, 10 to the minus 6, 10 to the minus 12, very, very, very small numbers. But I will use my assumption that assume this x, that I still need a value for x to solve for. It's going to be 1.54 times 10 to the minus 10. Square will stay the same, but this minus x, that this minus x is going to be so small that really I'm still left over with 0.100 of my benzoate. the conjugate base. Change in x is going to be the square root of 1.54 times 10 to the minus 10 times 0.100. And if you do that on your calculator, plug in 3.92 times 10 to the minus 6 here. 0.100 minus 3.92 times 10 to the minus 6 is still going to be 0.100. Okay? What's my concentration of equilibrium of benzoic acid, the acid? It's going to be 3.92 times 10 to the minus 6, like micromolar amounts, micro 10 to the minus 6. What's my concentration of OH minus? So that's x. Here's our x, 3.92 times 10 to the minus 6. Finally, we can solve for our pH. To do that, we'll solve for our POH. POH is minus the log of your OH concentration. We know our OH concentration at equilibrium is going to be 3.92 times 10 to the minus 6. And that is going to be my pH. That's my POH. So I'll use this relationship of pH plus POH is equal to 14. And pH now is going to be 14 minus the 5.40 that I calculated before. My pH of this solution is going to be, so that's what will happen when you react a weak acid with a strong base. The back reaction is going to influence your pH value. Okay, so we first started off with this. This is the original reaction. But at the equivalence point, all the strong base ate up acid, so we can't use the Henderson-Hasselbalch here. So we need to find a way to derive the pH. To derive the pH, we will do so indirectly by looking at the back reaction, constructing a second ice table assumption, and the assumption is very valid because our equilibrium constant for the back reaction is at 10 to the minus 10. And then backhandedly, we'll get the POH because the strong base is going to dominate. And from that, we will get the pH. Notice that our pH is above 7, so we would expect a basic solution, and we got a basic solution. So let's attempt this problem right here. It asks us the question of the pH of a titration of 25 mils of 0.200 molar C5H5N, that's pyrimidine, with the addition of 30 mils of 0.200 molar hydrochloric acid at the equivalence point. So we are asked to find the pH, and we are reacting HCl 0.200 molar. This is a strong acid, 30 mils of that, with 25 mils of 0.200 molar pyridine. And pyridine is not in our list of strong bases or strong acids. It's actually a base. It has a Kb value of, so it's going to be a base of 1.7 times 10 to the minus 9. 10 to the minus 9, that's pretty weak. Essentially reacting a strong acid with a weak base. The reaction that will happen when we mix these two together, C5H5N act with HCl. Our strong acid is nothing more than H+. All of this happens in water. H+ does what H+ does. Hydrochloric acid donates 100% of its proton, or close to 100% of its proton. It's a strong acid, to pyridine. And you have C5H5N+, and H+, excuse me. H+, you can use the hydromonium ion, and you'll see you'll have water left over. Let's figure out the concentrations after the mixing of these two. You have first the final concentration of pyridine, C5H5N, 25 mils, 0.200 molar solution of pyridine, reacted with 30 mils of a 0.200 molar. So our total volume, our final volume will be 25 plus 30, 55.00 mils. The mils cancel. Pyridine. Our concentration of HCl or H+, we have 30.00 mils. of a 0.200 concentrated solution of HCl. Our final volume after we mix the two is going to be 55 mils. The mils cancel. HCl, or hydromonium ion. So just as before in our situation where we have a strong base with a weak acid, here we have a weak base with a strong acid. Which do you think is going to get used up first? Well, this strong acid is going to neutralize the weak base in its entirety. And what will be left over? Well, what will be left over will be our fraction of H plus, 109 minus 0.0909, and that is going to equal to over concentration of H3O plus. That is going to contribute towards your pH. H is minus the log of the H plus concentration, minus the log of 0.0182. This particular case, where after the equivalence point we have an excess acid, and that excess acid that's left over, since it's a strong acid, you might as well just plug it into your pH equation. You don't need to use an ice table. 909 of this weak base will react with 0.0909 of the strong acid. Just going to neutralize all of this. It will just chomp at this weak base. It will do so until this weak base is no more, because it's a strong acid. What's left over is the residual that's going to remain in solution, and that's going to be the primary contributor towards the pH. Problem that I'd like to go over with you. Here we have a situation where we are mixing a strong base in NaOH with the weak acid, which is benzoic acid. We mix the two with their corresponding volumes and concentrations. We're asked to determine the final pH of the mixture. So let's first start off with writing the reaction that's going to happen. Equilibrium. That strong base emanating from the sodium hydroxide is going to really abstract that proton. Or you can state in the flip side that weak acid is going to donate that proton to the hydroxide ion. This abstraction is going to be very strong. This donation is going to be very weak because acetic acid is a weak acid. Either way, benzoic acid is a weak acid. Either way, you will wind up with the conjugate base benzoate. So that is the net reaction. Let's figure out the final concentrations that will happen after you mix these two together. So we are starting off with, let's first do the concentration of OH minus. We're starting off with 10 mils, a 0.200 molar solution of OH. With those 10 mils with 25 mils of the weak acid. So 10 mils put into a mixture that has 25 mils gives us a total volume of 35 mils. 10 plus 25. The mils cancel, hydroxide ion. The concentration of benzoic acid, we took 25 mils out of a bottle whose concentration is 0.200 molar. So we took 25 mils whose concentration of benzoic acid is 0.200 molar. Our total volume after mixing the two reactants is going to be 35 mils. The mils cancel. All right, so now let's contrast this situation with what we had before. Before, we had an excess of our strong acid or strong base. Here, we have of our weak acid. Can we do straight up that all of the hydroxide 0.0571 will react with 0.0571 of the weak acid? We can do that, but I'd like to show you another way. Let's do this reaction using the Henderson-Hasselbalch equation. For our conditions, we calculated the final concentration of OH minus is 0.0571, and we calculated the final concentration of benzoic acid is 0.143. Into our ice table, as we stated before, all of the strong acid gets eaten up because it's a strong acid. We'd expect none of that to remain. That is to say, we would expect all of this OH minus to pick up all of this proton from benzoic acid. So that will be limiting. This will be plus 0.0571 in the product side. We really don't care about water here. So at equilibrium, we will have 0.143 minus 0.0859 molar. And at equilibrium, we will have 0.0571 benzoate. So let's use the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of A minus, the conjugate base, over the conjugate acid, that ratio. pKa of benzoic acid, the pKa of benzoic acid, the propensity to give off that proton is 6.5 times 10 to the minus 5. It's going to equal to minus the log of 6.5 times 10 to the minus 5 plus the log. What's our concentration of the conjugate base at equilibrium? 0.0571. What's the concentration of my conjugate acid at equilibrium? 0.0859. So this is a ratio, the units cancel, and that's going to be my final pH. This is how I would do it on my calculator. I would do 0.0571 divided by 0.0859. That equals to log that ratio minus 0.177. You may want to just write that down. Minus the log of 6.5 times 10 to the minus 5. So 6.5 times 10 to the minus 5. Log that and minus that, so get rid of that minus sign. 4.18. So 4.18, be careful of your signage here. 4.18 minus 0.177 is going to be 4.01. Is going to be key here, but you notice that I don't use my pH equation or my pOH equation. Why? Because I don't have any. It gets all subsumed. And one contributor towards my pH is the acid going in this direction and the base going in that direction. Also occur with a solid. We call that a KSP, a solubility product constant. In that situation, the precipitate or your solid is in equilibrium with its component ions. So when we do our KSPs, because it is products over reactants, we actually write the reaction in the reverse direction. So generally we write our KSPs like this. It is in an equilibrium with copper ion, lead ion. Easily put our KSP value, reactants. Remember, we can't put solids in our equilibrium constant. So when we write our equilibrium expression like this, our KSP now becomes concentration of copper ion in solution times the concentration of hydroxide ion in solution, but we have to square it. The square comes from this term. Sparingly soluble compounds or solids, or whenever you see a solid that is in equilibrium, you want to write it like this. A, we don't call it KB, we don't call it KW, it's KSP, the solubility product constant. So we can plug this in here into this equation to get what we call the solubility. Now when we use our ice tables, we are not using X, we are using S for solubility because we are concerned with how much of copper is soluble, how much of the hydroxide is soluble in a equilibrium that contains a solid. Solids do not go into our equilibrium expression. KSP expression, this is going to be the reaction that describes that KSP. Don't forget the law of mass action tells you that you have 2 moles of this ion, so that 2 becomes a square in the KSP expression. And instead of X, we will have S's. Initially, we will have 0 of this and 0 of that. Some of this copper hydroxide will go to make copper ion, so we'll call it plus S. And some of it will go and make hydroxide ion plus 2S because there's 2 moles. So at equilibrium, we'll have some solubility of copper that goes in solution, dissolved in water, and then we'll have some solubility of hydroxide ion that goes back into water because we have an equilibrium between the solid and its component individual ions. So let's plug these equilibrium terms back in here. So our KSP value, as denoted in the text, is 2.2 times 10 to the minus 20. That's a very, very small number, but we still have, I guess, an insignificant amount that's going to go into copper ion and hydroxide ion. At equilibrium, copper ion will be S, and at equilibrium, hydroxide ion in solution, dissolved in water, will be 2S. We have to square that. So this S times 2S squared is actually 4S cubed equals 2.2 times 10 to the minus 20. So S is going to equal to the cube root of 2.2 times 10 to the minus 20 divided by 4. So that S stands for solubility. In order to do this on your calculator, what you can do is, now my calculator actually has a cube root symbol. You can see it. For those that don't have that cube root symbol, you can take it to the power of 1/3. In other words, on your calculator, you can do 2.2 times 10 to the minus 20 divided by 4. Raise that whole fraction to 1/3. Get the same answer. So I'll do 2.2 exponent minus 20. Or that's my answer. So what I'll do is I'll raise it to the 1/3 power. So that little bracket, I'll put that here, and I'll put parentheses 1 divided by 3. Or I can do 0.333333. And I get 1.77 times 10 to the minus 7. Be cognizant of your units. The units here are going to be molar, okay, because concentration has units of molarity in this particular case. So 1.77 times 10 to the minus 7 molar, or moles per liter. Per liter remain in solution. 10 to the minus 7 is it's a pretty small amount. Now if you want to get it to grams per liter, you can just multiply it by the molecular weight and do that corresponding conversion. So the solubility of copper ion in copper hydroxide solid is 1.77 times 10 to the minus 7. The solubility of hydroxide ion that goes into solution in a copper hydroxide precipitate is going to be 2 times 1.77 times 10 to the minus 7. So roughly about 3.4, 3.5 times 10 to the minus 7 is your solubility. The solubility of copper ion and hydroxide ion in water by itself, by virtue of its KSP. What happens if you take some of that solid copper hydroxide and dump in copper nitrate? So the exact same situation occurs here. We have our KSP being a sparingly soluble solid is in an equilibrium with copper ion and 2 hydroxide ion. So we'll do our ice table before. We won't use X, we'll use S for solubility. But now we have 0.0100 molar copper nitrate. So you remember all nitrates are soluble. So in essence, the copper ion concentration is now going to be 0.0100. So in our ice table, the copper ion is not going to be 0, but 0.0100 molar as a result of the copper nitrate dissociating into copper ion and going to be 0.0100 molar. Mole, the coefficient here is 1, so if the coefficient was 2, we'd multiply this by 2, but the coefficient here is 1, so in this balanced dissociation equation. So our initial concentration is 0.0100 molar. And our initial concentration of hydroxide, since we're talking about this reaction going this way, will be 0. And our change is going to be plus S plus 2s. Okay, it's going to be plus because we're talking about solubility and how much of this solid is going to go back into making the component ions. So our new equilibrium concentrations are going to be 0.0100 plus s for the copper ion and 2s for hydroxide ion. So let's plug that into our KSP expression. KSP is going to equal to copper ion in solution times the hydroxide ion in solution. Okay, this is an easy point to make a mistake upon, the law of mass action. Here, our concentration of copper ion in solution at equilibrium is 0.0100 plus s. Our concentration of hydroxide ion is going to be 2s. That whole thing is squared. So I'll assume that my s is going to be small. Now how can I make my assumption? Value at 25 degrees is 2.2 times 10 to the minus 20. So it's going to stay here and very little of it is going to go to the right towards the component ions. But there's enough that we can probably try to determine how much of it does go back into solution. So 2.2 times 10 to the minus 20. I'm going to make my s small and realize that most of my copper ion will probably be 0.0100. Very little of that copper ion will come from this reaction going this way to generate copper in solution. So 2.2 times 10 to the minus 20 is going to equal to, assuming s is small, is going to equal to 0.0100 times 2s squared is nothing more than 4s squared.
4s squared.
So 2.2 times 10 to the minus 20 divided by 0.0100, that times 4. You want to take the cube root.
Square root.
And that's going to give you my new solubility. So let's put those numbers in and see what we get.
7.4 times 10 to the minus 10
is my new solubility. So the solubility of copper hydroxide in the presence of copper nitrate is going to be 0.0100 plus 0.8.
7.4 times 10 to the minus 10.
It's essentially going to be 0.0100, right? Take 0.0100 plus something that's 10 to the minus 7. It's still going to be 0.0100. My solubility of hydroxide ion in copper hydroxide is going to be 2 times
7.4 times 10 to the minus 10.
So whatever 2 times that's going to be. So complex ions, you saw that when you were doing the experiment on Le Chatelier's principle, particularly iron thiocyanate at the copper ammonia complex. Here, that same copper hydroxide whose KSP you've measured and whose solubility you've measured in water and in copper nitrate can form a complex with ammonia. And that Kf, we introduce a new equilibrium term here, Kf. It's not KSP, it's not Ka, it's not Kb, it's not Kw, but it's Kf. And that formation is 5.0 times 10 to the minus 10 to the 13, positive 13. So we would expect this to be a very, very conducive reaction in terms of forming this complex ion. Usually complex ions are colored in solution, brilliant red or brilliant blue. Now we want to know what is the solubility of copper hydroxide in this ammonia NH3 solution. And so we will give you the formula for that. You do not need to know this reaction per se in terms of, copper NH3 complex plus 2. You don't need to know that. We'll give you this equation. The Kf value is going to be 5.0 times 10 to the 13. And when I say we'll give you this equation, you'll have to come up with the equation. You don't have to know the formula of the complex ion. So that equilibrium strongly favors the product side, 10 to the 13. And then we have copper hydroxide, which we know is a sparingly soluble solid. So we have this back and forth reaction occurring here of 2.2 times 10 to the minus 20. So if we add these two reactions together, the copper ion will cancel out with the copper ion, and then our net equation hydroxide, which is in an equilibrium with its component ions, reacts emulsion. This is in an equilibrium to give you your complex in solution. Is going to be when you add two reactions, you multiply equilibrium constants. When you add reactions, you multiply their equilibrium constants. So our new K value is going to be, I'll just call it K prime, is going to be Kf times Ksp, which is 5 times 10 to the 13th. That's a very, very forward-going equilibrium reaction multiplied by a equilibrium constant that is very, very non-forward going, favors the reactant side. There's the reactant side. It's not strongly favored in the formation of the complex ion because you're starting off with a sparingly soluble solid that likes to remain in solid form, Ksp 2.2 times 10 to the minus 20. Stability of this copper ammonia complex, so that's going to be 0, and hydroxide is going to be 0. So the reaction is going to go this way. We want to figure out how much ions in solution are going to form. So this will be minus 4s. This would be s. This would be plus 2s. So in equilibrium, we'd have 0.0100 minus 4s of the ammonium ion. Notice this is dominating, 0.0100. Our complex ion concentration of s, and by virtue of 2 moles of hydroxide being formed, our solubility in solution is going to be 2s. So let's put that into our K value via the law of mass action, products over reactants. Do not forget that 2 comes from the fact that in our balanced chemical equation we have 2 moles of hydroxide that's being formed. The K value that we've computed was 1.1 times 10 to the minus 6, the formation of that complex ion in copper hydroxide. And our equilibrium concentration of hydroxide ion was 2s. We square that. Our equilibrium concentration of this complex ion is going to be s. Concentration of ammonia is going to be 0.0100 minus 4s. And all of that gets computed to the 4th power. Here we just plugged in these values to our corresponding equilibrium equation, the balanced chemical equation. So now let's solve for S, or solubility. I'm going to assume S is small, or the small. Get 1.1 times 10 to the minus 6. And I'll just remove that to the power of 4, and I'll remove that 4s. Essentially doing is saying that this minus 4s, that s term is going to be insignificant because I have a K value of 10 to the minus 6. So what I'm really solving for is s and 2s, and this minus 4s is going to be so small, the concentration of my ammonia is really going to be dominated by the 0.010 molar that I've added to my copper hydroxide, where times s is 4s cubed divided by 0.0100. So my solubility S is 1.1 times 10 to the minus 6 times 0.01. Divide that by 4, and I'll take the cube root of that to give me my solubility of hydrogen, which will be 2s, the complex, which would be S, and then the solubility of my ammonia, which would be 0.100 minus 4s. So plugging that into my calculator, I get a value of 4 times 10 to the minus 3, 30. And that will be my answer. So the question, let's go back to our question here. The question is asking for the solubility of copper hydroxide in 0.0100 molar NH3. In 0.0100 molar and a value of S. Our value of S was 1.40 times 10 to the minus 3 molar. Solubility now is going to be S 1.40 times 10 to the minus 3 of the copper ion. And its solubility is going to be 2 times that, which would be 2.80 times 10 to the minus 3 molar.